And indeed, I'm talking about the sort of a rather dramatic sounding title about the end of space-time. But it's not really hyperbole. We are at a point in the development of fundamental physics. I think a lot of people feel, which is the kind of thing that happens on the sort of once a century timescale in this business, where the fundamental principles that by now we're spectacularly successful at describing everything we see in the real world from the tiniest distances we're probing at accelerators like the Large Hadron Collider, 1,000 times smaller than the nucleus of the atom, all the way out to the size of the observable universe, 10, 15 billion light years across. There's a set of ideas and principles that were handed to us by the revolutions in the first part of the 20th century, which were these revolutionary developments of the principles of space-time and of quantum mechanics, both of which, of course, have huge contributions from German physics and physicists. And these twin principles turn out to be astonishingly restrictive in how they allow us to talk about consistent laws of nature on the one hand, and astonishingly powerful on the other. And it's indeed essentially these principles and not much else that goes into giving us a menu of possibilities for what the world could possibly look like, and a particular combination, the sort of theoretical framework that lots of talk about, laws of physics that are compatible with quantum mechanics, the principles of quantum mechanics in space-time is known as quantum field theory. So that's a sort of a large theoretical framework that lets us talk about possible laws of physics. And there's a particular quantum field theory. It's a famous standard model of particle physics and cosmology that describes everything we see in the world around us over the huge range of distances that we just talked about. So we're in a situation where our existing principles handed from these revolutions are astonishingly powerful, and they work, but we have strong suspicions that the next step in physics has got to pull the rug out from under us and has to remove some of these principles from their primary role in the description of physics. And maybe this statement is a statement which most theoretical physicists who have thought about this problem would agree with, that certainly the notion of space-time is likely an approximate one and won't survive in a more the next complete description of physics. And this is because of some very simple thought experiments that we can do that have to do with the presence of both gravity and quantum mechanics. So the slogan is that because of gravity and quantum mechanics, the notion of space-time is doomed. So why is that? So let's imagine doing a few simple thought experiments. So I'm a terrible artist, so you're going to have to tolerate my terrible art in this talk. This is supposed to be a magnifying glass, okay? But let's say I'm going to use this magnifying glass to try to look at some small region of space and time, just to see what's there, just in the vacuum. Now, because of quantum mechanics and Heisenberg's uncertainty principle, in order to look at shorter and shorter distances, literally to look, I'd have to look at it with light with shorter and shorter wavelengths. That would have higher and higher frequencies. And in quantum mechanics, that would tell us that the minimum energy that I would need to probe very short distances has got to actually get larger and larger. So in order to probe shorter and shorter distances, we need to put more and more energy into a smaller and smaller region of space. That's the explanation for the huge irony why gigantic particle accelerators like the Large Hadron Collider, which are 27 kilometers around, are what we have to use to study nature at the tiniest distances we've ever probed. We need the biggest machine to probe the tiniest distances ever, precisely because of this business about the uncertainty principle. But anyway, in a world without gravity and infinite funds, you just ask governments for more and more and more money, and you can probe arbitrarily short distances by going to arbitrarily high energies. But in the actual world, we have gravity, and something very bad happens at some point. You put so much energy into such a tiny region of space that Einstein tells us that E equals mc squared. So it's like putting an enormous amount of mass into a tiny region of space. And you know what happens when you put a huge amount of mass into a tiny region of space? You collapse the region you're looking at into a black hole, and no information can possibly get out of it. So your act of trying to look at very tiny distances instead produces a black hole that makes it impossible to see what's going on in there. And if you try to do this with an even more powerful microscope, an even higher energies, what happens? You make an even larger black hole. So your attempt to probe shorter and shorter distances stymies itself, and it's simply impossible to give operational meaning to distances and times that are small enough. Now, the relevant distances and times involved here are tiny, 10 to the minus 33 centimeters, times of order 10 to the minus 43 seconds. That's how long it takes light to traverse a distance of 10 to the minus 33 centimeters. And the fact that, just to compare, the size of the atom is 10 to the minus 8 centimeters. The size that we're probing at the Large Hadron Collider is 10 to the minus 17 centimeters. So we're a long, long way from probing this directly experimentally. Nonetheless, we can do this thought experiment, and we see that something new has to happen. And every time it's happened to us before in physics, that we can't even in principle give operational meaning to some concept. In this case, we're trying to give operational meaning to space and time. It's meant that that concept doesn't actually exist. And in the more complete definition of physics, it won't be there. And somehow it will arise as an approximate emergent phenomenon from more primitive building blocks. Now, where do these questions become important? Well, there's a few obvious places where this kind of question becomes important. For example, we know the universe is expanding, so if we run the picture of the expanding universe back in time, it's contracting, getting hotter and hotter, denser and denser. And there's the moment that we colloquially refer to as the Big Bang, where the curvatures are of the universe and the temperatures and everything is at this ridiculous scale we're just talking about on the previous slide. Now, sometimes people ask what happened at the Big Bang or before the Big Bang, and we don't know, because what's going on is that the whole notion of before is breaking down. The whole notion of time is breaking down around the Big Bang. So it's not even clear if the words make sense, what happened before. Similar things happen if you throw yourself into a black hole. If you cross the event horizon of a black hole, then what happens inside isn't like you hit a point that's sitting there, but it's like being on the inside of a collapsing universe, and it's like running this picture of the expanding universe in reverse, and you get sort of crunched in your future at some point. Again, we don't know what happens there. So these are just places where our theories simply break down. There are well-posed questions that we can't give answers to, and they break down when quantum mechanics and gravity both become dominantly strong. Now, there's been a lot of work over the past 30, 40 years thinking about this problem from various points of view. One of the remarkable developments that would be a whole series of colloquia on its own that I won't say anything about in detail today, but just to show you the sort of unity of concepts and ideas in physics, is that around a little over 20 years ago, string theorists realized that we could think about this idea of space-time emerging from more primitive building blocks, at least in a first toy setting, where you can see that space can emerge from building blocks that don't have space in it. And physicists love to put systems in boxes. And so what you want to do, if you're studying this kind of fundamental question, is consider a whole universe in a box. And there's a way to talk about a universe in a box where the inside of the box is a very curved space. So you can really think of this as a tin can, the way it looks like in this picture. But the geometry on the inside of the tin can is curved in an unusual way, so that the distance from any point on the inside to the walls of the tin can is infinite, but it takes light a finite amount of time to bounce off the walls. So this kind of unusual geometry is known as anti-de Sitter space. And physicists realized that if they could imagine experiments that were done on beginning and ending on the walls of the space, just pinging the walls of the box, then you would imagine what's going on. You ping the walls, some waves come crashing in, they go crashing back out, you measure what happens out as a function of what you threw in. But they realized that they could give a description of what happened here without ever mentioning the existence of the interior, only talking about ordinary interactions of particles that live on the walls of this box. And in a very concrete sense, the inside of the box kind of emerges out of the dynamics of thinking about the very strong interactions of particles that only live on the walls of the box. When the interactions between these particles are very strong and you can't follow what each one of them is doing individually, there's an effective description of what's going on that makes it look as if there's an interior, with space in the interior, gravity in the interior, even strings in the interior. But fundamentally, there's just sort of particles interacting very, very strongly on the walls. So this is a first example where out of a quantum mechanical system with very, very strong interactions with particles emerges space and gravity in the interior. And there's the whole general idea is known as holography. It's something like the colloquial picture of a hologram, which is a fundamentally two-dimensional thing, but which encodes three-dimensional information. And there's many aspects of this dictionary. I'll just mention one of them, one of the most basic ones. If someone told you, look, this interior space here really doesn't exist, everything is sort of living on a screen out there, you would say, what the heck are you talking about? I could have this purple ball and the green ball, and one of them is here and the other one's further out. So what could it possibly mean that they're in different positions here if this space isn't really there? And the answer is that the purple dot in this description is described by some kind of fuzz of energy of some size in the wall description. And as you move the purple dot to the green dot, that corresponds to changing the size of the ball. So somehow the position in this extra space is encoded by the size of excitations in this hologram. So that just gives you some idea how the information, which is sort of lower dimensional, can encode in it properties that we ascribe to the presence of space, and when you study it further, gravity and lots of other things coming out as well. Okay, so this is a huge subject that's being studied intensively, continues to be studied intensively. But the world in a tin can is not our world. Okay, we don't live in a tin can. Very important about this tin can is that it's infinitely old. It's a tin can that lived forever. It will live forever into the future. And most of the interesting questions about our universe, most of the literally existential questions about our universe are cosmological ones. They have to do with the fact that our universe was born at some point. We'd like to know how our universe was born, what it means that our universe was born. We want to know something about the fate of the universe in the future. All of these questions involve the notion of time in a crucial way. And I probably don't have time to talk about this in a detail, but there are some questions about the birth of the universe at the Big Bang that are mysterious. There is a whole Pandora's box of questions that perhaps in a question session I'll say something more about if people ask, about something that astronomers discovered in the late 1990s, that the universe is not only expanding, but the rate at which it's expanding is accelerating. It's doubling in size at a constant rate every 10 billion years or so. And this fact that the universe is accelerating opens a huge number of conceptual mysteries on us in physics. And all of these ideas, both the notion of time plays a really crucial role, and for a variety of reasons, it looks like, especially if the notion of time goes away, somehow a lot has to change about our understanding in physics, but especially the things that are crucially tied into our descriptions of quantum mechanics also have to be modified in some way. So that's kind of a clue from far in the future that we have to eventually understand the emergence of time, and very likely not just the emergence of space-time, but very plausibly some kind of deeper rubric out of which both space-time and quantum mechanics emerge.